Так, давайте для начала объявление-напоминание. Ну, я сперва по-русски скажу, потом переведу при необходимости. Значит, я об этом уже говорил, на всякий случай хочу напомнить, что на следующей неделе у нас коллоквиум. Коллоквиум будет онлайн по понятным причинам. Вот, подробности я разошлю в общей рассылке, буквально вот на днях.
Вместе с билетом.
Да, билет я повешу на страничке, но на самом деле там отличие от того, что уже написано, там же краткое содержание каждой лекции-то есть, отличие будет минимальное. Может, как-то будет разгруппировано, но в целом это приблизительно то же самое, что там уже есть. Вот, но я повешу, конечно, да, повешу программу коллоквиума. Значит, коллоквиум, тема коллоквиума — это все до Гильбертовых пространств включительно. То есть то, что сегодня уже в коллоквиум не попадает, это будет уже на экзамене.
То есть через неделю не будет, а будет онлайн-коллоквиум?
Да, будет онлайн-коллоквиум, начиная с 11:10. Вот. Ну, в общем, всякие технические подробности, там, как подключаться, то да сё, это я все напишу.
А из-за этого расписание семинаров сдвинется на неделю? Прием задач и семинар? Да, конечно. Раз на следующей неделе у нас коллоквиум на пару, то прием задач сдвигается. Вот. Это я тоже напишу. Там, на самом деле, у нас же еще одна группа будет, семинарская. Вот, я там посмотрю еще разочек в понедельник, там, вторник или какой-то. Я сейчас уже забыл, за какой день там было большинство голосов. В общем, вторая группа еще будет по семинарам, какой-то из где-то ближе к началу недели, начиная со следующего модуля, то есть уже после коллоквиума. Вот. Okay, so should I translate this in English? So next week we have a midterm exam at 11:10, and it will be online. The details will be sent in a few days. So the Zoom link and all technical details will be. So I'll send them to everybody. And the program will be available at the website of the course. And starting from the next module, that is from the 9th of November, there will be two groups for exercise classes. So the first group will remain at the same time, so at 12 at 1 p.m. On Thursday, and another group will be probably on Monday or Tuesday, I don't remember exactly. But anyway, I'll send this information fairly soon. Okay, so let's now speak about mathematics. Today, our next strategic goal will be to discuss duality for normed spaces. So to begin with, let's introduce some terminology. Suppose that we have a normed space, X, and as before, we assume that the base field, bold K, is either the field of real numbers or the field of complex numbers. And by definition, the dual space, or more exactly, the topological dual, the topological dual space of X is the space of all bounded linear maps from X to K. And the space is denoted by X star. Elements of the space are called bounded linear functionals. Elements of X star are called bounded linear functionals on X.
this space is sometimes called a topological dual in order to distinguish between this space and the algebraic dual, which consists of all linear functionals, possibly unbounded linear functionals on X. But nevertheless, the notation is the same as for the algebraic dual. Usually this doesn't lead to any confusion. And I always call this space just the dual of X. In Russian we say either либо двойственное пространство, либо сопряженное пространство. Оба термина встречаются приблизительно одинаково часто. So what can you say about this space? First of all, let's observe that the dual space is always a Banach space. It is always complete. Well, indeed, we know that if X and Y are norm spaces and Y is complete, then B of XY is also complete. But since the base field is complete, it follows that X star is also complete. What else can we say about the space? Well, the correct answer at this point, the correct answer is we can say nothing about X star. In particular, it is not obvious at all that the space is non-trivial. That is, it is not obvious that there exists at least one non-zero bounded linear functional on X. In fact, X star is indeed non-trivial, and moreover, it is rich in the sense that the elements of X star separate the points of X. And this will follow from the Hahn-Banach theorem, which is one of the basic principles of functional analysis. So our next goal is to discuss the Hahn-Banach theorem. So suppose that we have a semi-normed space, X, in fact, we will mostly apply this theorem in a situation where X is a normed space, but sometimes, and especially in the next term, in the course of operator theory, it will be essential to have this theorem for semi-normed spaces also. The proof for semi-normed spaces and for normed spaces are absolutely identical to each other. So suppose that X is a semi-normed space and X0 is a vector subspace of X. So the Hahn-Banach theorem is about extending of linear functionals from X0 to X. So suppose that F0 is a linear functional on X0, and we suppose that F0 is dominated by the semi-norm, in the sense that it satisfies such an estimate. Then there exists a linear functional F defined on X, a linear functional on X, which extends F0. So the restriction of F to X0 is F0, and such that F satisfies the same estimate everywhere on X. The essence of this theorem is here, is on this estimate. So without these two estimates, the theorem would be trivial. So if we just want to extend a linear functional from a subspace to the whole space, we just take another vector subspace x1, such that x is the direct sum of x0 and x1. So this is always possible by some standard result from linear algebra. And then we let f to be, we define f to be f0 on the first summand and identically 0 on the second summand. And that's it. So the point is that we can extend f0 in such a way that the same estimate which holds on x0 holds on x as well. Our strategy for proving this theorem will be as follows. First, we prove this theorem for the real case, that is for the case where the base field is the field of real numbers, and then we reduce the complex case to the real case. So let's first prove this for the field of real numbers. First of all, we discuss a very special case, case 1. This is the case where x0 is a codimension 1 subspace. So we suppose that there exists an n0 vector y such that x is the direct sum of the one-dimensional space spanned by y and x0. So this is a case where x0 is a hyperplane in x. Well, in this case, it's absolutely clear how such an extension can look like. So it's clear that for each real number c, there exists a unique linear functional f on x such that f extends f0 and such that f of y equals c. So to construct an extension from a codimension 1 subspace, it's enough to specify this extension on a single vector y. So our goal is to find c in such a way that this estimate holds. So what we want to do is to find c such that we have the following inequality. Well, let's now write this inequality in a slightly different but equivalent form. So this inequality is equivalent to the following: f of y minus x is less than or equal to the semi-norm of y minus x for each x in x0. Well, this is more or less equivalent to this inequality by linearity. So each element from x has the form lambda y minus little x from x0, and we can divide by lambda by linearity of f. Okay, so now this left-hand side can be written as follows: f of y is c, and f of x is f0 of x, because f extends f0. So this is equivalent to the following double inequality. So c is less than or equal to f0 of x plus the semi-norm of y minus x. And on the other hand, c is greater than or equal to f0 of x minus this number. For each x in x0. So we want to prove the existence of c satisfying this estimate. Let's now observe that such a constant c exists if and only if for each pair of elements x1 and x2 in x0 we have the following: f0 of x1 minus y minus x1 is less than or equal to f0 of x2 plus y minus x2. Well, why is it so? Well, the one direction is clear. If such a constant C exists, then this number is less than or equal to C, and this number is greater than or equal to C. And we have this. And conversely, if we have this inequality, then we can let C denote, for example, the supremum of the left-hand side. Over all x1 in x0. And if C is defined by this formula, we get this double inequality. Okay, so we want now to show that F0 satisfies this estimate. Well, this is more or less clear, because by assumption, if we apply F0 to x1 minus x2, this will be less than or equal to the norm of x1 minus x2 because of this inequality. And by the triangle inequality, this is less than or equal to x1 minus y plus y minus x2. And the resulting inequality is easily seen to be equivalent to this one. So we take this from here to here, and this from here to here, and we get this. So this is equivalent to, well, let it be inequality star. I have no room to put the star here. So this is inequality star. Okay, so we conclude that F0 satisfies this estimate. So the constant C, for which this inequality holds, exists, and the required extension is constructed. So this completes the proof of case 1. The general case is in fact easily reduced to case 1. This is a standard application of Zorn's lemma. So case 2 general. Excuse me. So let's consider the following set that's denoted by M. This set consists of all extensions of F0 satisfying this estimate of all extensions to some bigger subspace. So formally it consists of all pairs Z and G, where Z is a vector subspace containing x0, and G is a linear functional on Z, such that G extends F0, and such that G satisfies this estimate everywhere on Z. So this is the set M. It's non-empty because x0 and f0 are in M. It's a standard argument shows that M satisfies if we equip M with the order relation, so it becomes a partially ordered set. Well, maybe I have to say this a little bit more formally. So let's introduce the following order relation on M. So we say that a pair Z1, G1 is less than or equal to the pair Z2, G2 if Z1 is contained in Z2 and if G2 extends G1. So this is a natural order relation on M. And if we equip M with this order relation, it becomes a partially ordered set. A partially ordered set. And the standard argument shows that the set satisfies the conditions of Zorn's lemma. This is a little exercise. So, in other words, each chain, each linearly ordered subset of M has an upper bound. Indeed, if we have such a chain, set Zi, Gi, we just take the union of all the subspaces in the chain, and we define the functional on this union such that the restrictions of this functional to the respective subspaces agree with the functionals Gi. And so this shows that this set indeed satisfies the conditions of Zorn's lemma. So it has a maximal element. So there exists a maximal element, say Z and F. And I claim that Z is actually the whole of X. I claim that Z equals X. Well, why is it so? If not, if Z is strictly smaller than X, then we take any element in X which is not in Z, and consider the direct sum of Z and the one-dimensional space spanned by Y. So let Z1 denote the direct sum of the following two spaces. So Z has codimension 1 in Z1. And we apply case 1. So by case 1, there exists a linear functional f1 on Z1, which extends f and such that f1 satisfies the same estimate. So in other words, the pair Z1 f1 is an element of the same set big M. But this is a contradiction. This contradicts the maximality of this element. So this is a contradiction, and we conclude that Z equals X. So our functional f is the extension we are looking for. This completes the proof of our theorem. In the case where our base field, the base field is the field of real numbers. Okay, let's now look at the complex case. So we want to reduce the complex case to the real case. We will need the following simple lemma. Suppose that X is a vector space over the complex numbers. We introduce the following standard notation. So we denote by XR essentially the same vector space X, but considered as a vector space over the real numbers. Well, clearly, each complex vector spaces can be made into a real vector space in a trivial way. So this is the so-called realification of X. And we consider the following two vector spaces. The first vector space consists of all complex linear functionals on X. And the second space consists of all real functionals on the realification of X. That is basically on the same space X. And we have a natural map from the first space to the second space. It's denoted by alpha. So alpha takes each functional f to its real part. So it's clear that the real part of a complex linear functional is a real functional. So I claim that alpha is a bijection. Alpha is a bijection, and moreover, we have the following explicit formula for the inverse map. Alpha inverse of G is given by the following magic formula. Well, the proof is straightforward. Just a little elementary computation, and I leave it as an exercise for you. So we have to check that this formula indeed defines a complex linear functional. Obviously it is a real linear, but it is also a complex linear. It's a little calculation. And again, a little calculation shows that alpha and this map are indeed inverses to each other. Okay, let's now come back to the Handball theorem. And let's prove this theorem. Over the complex numbers. It's in the case where the base field is the field of complex numbers. So we have a complex linear functional f0 on x0, and we take the real part of it. So let g0 be the real part of f0. This is a real linear functional on x0. And it's immediate from the conditions of the theorem that G0 satisfies the same estimate as F0. Simply because the real part, the modules of the real part of G is less than or equal to the modules of G. We already know how to extend G to the whole of X. So the theorem is already proved over the real numbers. So we already know that there exists an R-linear functional G from X to R, which extends G0 and satisfies the same estimate on X. And now we construct a complex linear functional from G by means of this lemma. So let f be alpha inverse of G. This is the functional denoted, the functional defined by this formula. So by lemma, f is complex linear. And well, since G0 is a real part of F0, and alpha inverse are inverses of each other, we conclude that f0, f extends f0 by lemma. So to complete the proof, we have to show that f satisfies the same estimate. Well, to prove this, we take any element, little x, and we write the absolute value of f of x. Oh, sorry, we write f of x in the following form, where phi is a suitable real number. Of course, it depends on x, but x is fixed at this point. So now we see that f of x has the absolute value of f of x is f of x multiplied by e to the power minus I phi. That is, by linearity of f, this can be written as follows. And here I can now replace f by g. I can replace f by g because this number is real and moreover it is non-negative. So, but for g we have this. So this is less than or equal to the norm, to the semi-norm of this vector. And of course this is the same as the semi-norm of x. And that's it. So we see that f satisfies the same estimate. And this completes the proof.
Excuse me, how will replace f by j?
Well, look, this is real, of course, because this is the absolute value. So this is also real because they are the same. And g is the real part of f. This is f, and this is g. So this guy vanishes. G is the real part of f, but f is already real at this vector.
You mean that g of ix is 0 because ix is...
Well, this is 0. This is 0 because this is real.
Okay.
So if we take the absolute value of a complex number, we get a real number. Okay?
We can replace f by j and then tell that j is real.
No, the g is real, but the point is that after we have replaced f by g, we can apply this estimate for g. So we apply this estimate for g. So we get this. And these two numbers are the same because the modulus of this exponent is 1. Okay? So a little algebraic trick. We just somehow twist the original vector x, we multiply it by this number in such a way that the value of f on the twisted vector is real. This is the trick. Okay, so this completes the proof. And let's now look at some immediate corollaries of the Handball theorem. And there will be much more corollaries, so today we'll look only at some elementary corollaries. Corollary 1. Suppose that X is a norm space and X0 is a vector subspace of X. Then, for each bounded linear functional f0 on x0, there exists a bounded linear functional f on x such that f extends f0, and f has the same norm as f0. So each linear functional defined on a subspace of a norm space can be extended to a bounded functional on the whole space, and moreover the extension can be chosen in such a way that the norm is the same. Well, to prove this result, we take f0 and we observe that f0 of course satisfies such an estimate where C is the norm of f0. And now we just multiply the norm on X by the constant C, and we apply the Handball theorem. We apply the Handball theorem to X equipped with a new norm, where the new norm is the constant C multiplied by the original norm. And so we apply the theorem and we get the required extension f. So f will satisfy the same estimate on X, so this means that the norm of f is less than or equal to C, but of course it cannot be smaller than C because f is an extension of f0. So the norm of f can be only bigger than the norm of f0. But in our case, the norms are the same, because this estimate which holds on x0 also holds on x. Okay, corollary 2. Corollary 2. Suppose that X is an ordered space, then for each non-zero vector in X, there exists a bounded linear functional f on X such that the norm of f equals 1, and such that f of x equals the norm of x. So in particular, this guy is non-zero, because x is non-zero. To reduce this to corollary 1, we take the one-dimensional subspace spanned by X, and we apply corollary 1 to linear functional f0 defined on the one-dimensional space spanned by little x, and given by the following simple formula. So it's clear that f0 is bounded and the norm of f0 equals 1. And we extend it by using corollary 1, and we get the functional f. So the norm of f is the same, and f of x equals the norm of x. Corollary 2 readily implies that the dual space is big if x is a normed space and x0 and x1 and x2 are two different vectors in X. And there exists a linear functional f, a bounded linear functional f of x on X such that f of x1 is not equal to f of x2. In other words, bounded linear functionals separate the points on X of X. Well, corollary 2 readily follows from corollary 3 readily follows from corollary 2 if we apply it to x1 minus x2. We apply corollary 2 to x1 minus x2. The next corollary is just an equivalent way of writing corollary 2, but a very convenient equivalent way. So corollary 4, if x is a normed space, then for each element x in x, I have the following formula. The norm of x equals the supremum of the absolute value of f of x, where f runs over the closed unit ball of the geospace. So f is in x star, and the norm of f is less than or equal to 1. And moreover, this supremum is attained. So I can replace the supremum by the maximum. Well, this is equivalent to corollary 2. Of course, this supremum is less than or equal to the norm of x. But on the other hand, we know that there exists a functional f, which is on the unit sphere, and such that this number equals the norm of x. So this supremum is attained and is equal to the norm of x. This is corollary 2. Corollary 5. It looks a little bit more general than corollary 2, but in fact it is equivalent to corollary 2. So suppose that x is a normed space, and suppose that x0 is a closed vector subspace. It's a closed vector subspace of x. Then, for each element little x, which is not in the subspace x0, there exists a bounded linear functional f on x such that f vanishes at x0, the norm of f equals 1, and such that f of x equals the distance between x and x0. So in particular, this number is not 0. This number is not 0. So in the special case where x0 is the trivial subspace, corollary 5 becomes exactly corollary 2. But in fact, corollary 5 can be easily deduced from corollary 2 by taking the quotient modulo x0. So we do the following. We apply corollary 2 to a functional g, to the equivalence class of little x in the quotient. So we get a linear functional g on the quotient such that the norm of g equals 1, and such that g applied to this equivalence class equals the norm of x plus x0. Okay, so let's now recall that the norm of this element in the quotient is nothing but the distance between x and x0. This is the distance between little x and x0. And now to construct our functional f, we simply compose the g with the quotient map. So f will be g composed with q, where q is the quotient map of x onto the quotient. And this f is exactly what we are looking for. Well, indeed, it vanishes at x0, because q vanishes at x0. So f of x is g of this, that is this, f of x is the distance between x and x0. And the norm of f equals 1, because q is a coisometry. It takes the open unit ball onto the open unit ball. And so the norm of f is the same as the norm of g.
Do you recall how we define norm on the quotient space, and why do we need x0 to be closed?
Well, first I'll answer the first question. So this is actually this is the definition of the norm on the quotient.
And it is a norm.
And this is a norm provided that x0 is closed. In the general case, this is a semi-norm. But if x0 is closed, this is indeed a norm. So f satisfies all the conditions listed here, and this completes the proof.
But we can apply the Handball theorem to the semi-norm space, so it's actually not essential that x0 is closed.
So if x0 is not closed, then, if x0 is not closed, and if little x sits in the closure, then clearly it's impossible to find such a functional such that this is not zero. So this will be zero in this case. So formally we can apply this. But this will be zero. So that's the difference. So we cannot separate a non-closed subspace from a vector which sits in the closure. So we can apply this formally, but we get zero in the end.
Excuse me, you are writing for all x exists f, and f that we get is good for all x's because we are choosing f like distance from x to x0 or not?
No. This g depends on x. First we choose x, then we take the coset, and then we find g. But g, of course, depends on this element in the quotient.
So if we are taking just f of any x is distance from x to x0, it will not have a norm 1. Yeah?
It's not a linear.
It's not a linear.
You want to well, of course, if we apply to if we want this formula to hold for all elements, then it might be impossible for linear functional. So we first we fix a vector and then we find the functional. So it's impossible to find a functional which satisfies this equality for all vectors in this space. Okay, so now it's time to discuss dual operators. Dual operators. So the point is that the construction of taking the dual is natural, that is, it is functorial. It is defined not only on spaces but also on operators between them. So suppose we have two normed spaces, x and y. And suppose that T is a bounded linear operator from x to y. By definition, the dual of T is a map T star, which acts from the dual space Y star to the dual space X star, and it is given by the following formula. So T acts from X to Y, F acts from Y to the base field, so this composition acts from X to the base field. So it is a bounded functional on X. And so T star is indeed a map from Y star to X star. So in Russian we say, значит, говорим либо двойственный оператор, либо сопряженный оператор. Это более-менее синонимы этой ситуации. So what can we say about T star? So here are some basic properties. The following proposition gives us some basic properties of T star. First of all, I claim that T star is a bounded linear operator from Y star to X star, and moreover the norm of T star equals the norm of T. Property 2, if we take a linear combination of two operators, say S and T, and take the dual, then we get lambda S star plus mu T star. So here lambda and mu are numbers, and S and T are operators from X to Y. In other words, the operation of taking the dual operator is linear. Property 3, if we have a bounded operator T from X to Y, and the bounded operator S from Y to another norm space Z, then if we compose them and then take the star, this will be T star S star. And finally we have the trivial but essential property that if we take the identity map of X, then the dual of the identity map is the identity map of the dual. So properties 3 and 4 mean that the operation of taking the dual space and the dual operator is a functor from the category of norm spaces to itself, or to the category of bounded spaces, because the dual space is always complete. So this functor is additive by property 2, and it preserves the norm. So let's prove property 1. I want to show that T star is bounded and has the same norm as T. Well, first of all, it's clear from the construction that T star is linear. This is clear. And to show that it is bounded, we simply try to calculate the norm of T star. So we'll do a little calculation which will show that T star is indeed bounded and that the norm of T star equals the norm of T. So we simply write the definition of the norm. This is the supremum over the unit sphere, or over the unit ball, over the unit ball of the norm of T star F. Okay, let's now write explicitly the norm of T star F. So T star F is a functional. So the norm of T star F, so we write the same supremum. And the norm of T star F is the supremum over the unit ball of X. T star of F applied to X. And T star of X applied to F is F of Tx. Now we do a simple trick. We simply interchange these two suprema. This is clearly possible. So we get this. Oh, thank you. We interchange these two soups. So this will be supremum over x, and this will be supremum over f. Thank you. So why is it convenient? This is convenient because of this corollary. So we apply this corollary to the vector tx. So if we replace x by tx here, we see that this number, which is in brackets here, is nothing but the norm of t of x. So by corollary 4, so let me keep this here. By corollary 4, this is equal to the supremum of the norm of t of x. But this is nothing but the definition of the norm of t. This proves the first part of our proposition. So we proved that this number is finite, that is, t star is bounded, and that this number equals the norm of t. Okay, and parts 2, 3, and 4 are simple algebraic exercises, which are more or less immediate from the definition. Here's a simple corollary of this proposition. Corollary. Suppose that t is a bounded operator from x to y. Part 1. If t is a topological isomorphism, then so is t star. And part 2, if t is an isometric isomorphism, then so is t star. Well, essentially, these two parts are immediate from the fact that the operation of taking the dual is a functor from the category of norm spaces to itself. And moreover, maybe some of you still remember that actually we have two categories of norm spaces. In the first category, the morphisms are all bounded linear operators. And in the second category, the morphisms are linear contractions. That is, those bounded operators whose norm is less than or equal to 1. So formally, if you try to write this explicitly, the proof, say, of the second part looks as follows. We observe that T is an isometric isomorphism if and only if the norm of T is less than or equal to 1, and there exists a bounded operator S from y to x such that the norm of S is also less than or equal to 1, and such that ST is the identity map of x and TS is the identity map of y. So in other words, a linear map is an isometric isomorphism if and only if it has, or if and only if it is invertible. And moreover, T is a contraction and the inverse map is also a contraction. So these two conditions together mean precisely that T is isometric. And now, after we have rewritten the condition of an isometric isomorphism, we simply apply the star. Apply our star construction. And we see that the norm of T star is less than or equal to 1, and the norm of S star is less than or equal to 1, and S star and T star are inverses of each other by the previous proposition. And that's it. So S star, so T star satisfies all the same conditions listed here. So T star is also an isometric isomorphism. So this proves the second part of our corollary. And the proof of the first part is absolutely similar, and indeed it is even easier a little bit. So basically, this corollary is immediate from the fact that the star construction is a functor, and each functor takes isomorphisms to isomorphisms. What is much more interesting, and this will be proved a little bit later, that if X and Y are Banach spaces, then these implications are equivalences. So if a dual is an isomorphism, then T is also an isomorphism. But this is not trivial. This doesn't follow from abstract nonsense. This is a rather deep analytical fact. Okay, let's now look at some concrete examples of dual spaces. First of all, we will describe the dual of a Hilbert space. The dual of a Hilbert space. We'll start with a little observation. So let's observe the following. Suppose that H is an inner product space. And for each element y in H, we define a map Fy from H to the complex numbers by the following formula. This is the inner product of X and Y. Well, so the inner product is linear in the first variable. So this implies that Fy is linear. And the Cauchy-Bunyakovsky-Schwarz inequality implies that this number is less than or equal to the norm of y multiplied by the norm of x. So this means that this functional is bounded. So it is an element of the dual space H star. And moreover, the norm of Fy is less than or equal to the norm of y. In fact, if we substitute x equals y here and calculate Fy of y, this will be the norm of y squared. That is the norm of y multiplied by itself. So this is an equality now, and this means that the norm of y actually equals the norm of y. The norm of Fy equals the norm of y. So we see that each element in H determines a bounded functional on H, an element of the dual, of the same norm. It turns out that in the case where H is complete, that is in the case where H is a Hilbert space, all bounded functionals on H are of this form. And this is a so-called Rees representation theorem. So Frigyes Ries was a great Hungarian mathematician who was one of the founding fathers of on functional analysis. So especially his main contribution, well, he has made many contributions to functional analysis. Probably one of the main contributions is the theory of compact operators, which will be discussed at the end of our course. Okay, so suppose that H. Oh, sorry. Before we formulate this theorem, let us introduce a convenient terminology. So I'll give the following definition. If X and Y are two complex vector spaces or the complex numbers, and if we have a map phi from X to Y, then we say that phi is antilinear. Phi is antilinear if the following identity holds. So the difference between linear and antilinear is that we have lambda bar and mu bar, so the complex conjugates of lambda and mu. So now the Ries representation theorem tells us the following. Suppose that H is a Hilbert space. And consider the following map R from H to H star. R is for Ries. So R takes each element Y to the functional Fy defined here. So this map R is an isometric antilinear bijection. An isometric antilinear bijection. Well, sometimes we say that H can be identified with H star, but in fact this is not entirely correct for the reason that R is not an isomorphism in any reasonable sense. It is not linear, so it is not a morphism of our category. In fact, the truth is that there exist isometric isomorphisms between H and H star, but none of them is canonical. There are many isometric isomorphisms between H and H star, but they depend on the choice of a basis and they are not natural. And this map is, in a sense, canonical, but it is not linear. It is antilinear. So we already know from this observation that R is isometric. And it's clear from the construction that it is antilinear, because the inner product is not bilinear, but it is sesquilinear. It is linear, it is antilinear in the second variable. So we already know that R is isometric, and it's clear that R is antilinear. So to complete the proof, we have to show that R is surjective. We want to show that R is surjective. So let's take any element in the dual. Let F be an element of the dual. And let H0 denote the kernel of F. Let's also assume from the very beginning that F is non-zero. So H0 is a closed vector subspace of H, and we can apply the orthogonal complement theorem. So we can write as the direct sum of H0 and H0 orthogonal. This is exactly the place where we use the assumption that H is a Hilbert space. So this theorem holds for Hilbert spaces only. So what can you say about the orthogonal complement? A simple algebraic argument shows that the orthogonal complement is one-dimensional. Well, indeed, as a vector space, so we forget about the norm for a moment. As a vector space, H0 orthogonal is isomorphic to the quotient of H modulo H0. This follows from this formula, and the quotient modulo the kernel is isomorphic to the image as a vector space. But, well, F is a non-zero functional, and a zero-linear functional is surjective. So its image is the field of complex numbers. And so the dimension of the orthogonal complement equals 1. It is one-dimensional. And so we can take any element, any non-zero element little y in the orthogonal complement. And now our formula, this formula will have the following form. H equals H0 plus the one-dimensional space spanned by y. I claim that our functional f equals lambda fy for some complex number lambda. Well, indeed, first of all, we observe that if you take any complex number lambda, then both f and lambda fy vanish at H0. So f vanishes at H0 because H0 is the kernel, and fy vanishes because y is orthogonal to H0. So f restricted, so for each lambda, f restricted to H0 equals 0. And the same is true for lambda fy. So to show that these functionals are the same for some lambda, it suffices to find lambda in such a way that they agree at the single element little y. So hence these functionals are the same, even only if they are the same at y. Well, this is nothing but lambda multiplied by the norm of y squared. And this implies that we have the following equality. F equals lambda fy, where lambda is f of y over the norm of y squared. And so this element is in the image of R. So we conclude that R is surjective. This completes the proof. Well, maybe a final remark for today is the following. So let's look more carefully how we came to the Risk representation theorem. So we assumed that H is complete. And we know that for Hilbert spaces, that is for complete inner product spaces, the orthogonal complement theorem holds. The orthogonal complement theorem holds. And it is exactly in this place where we use the completeness of H. Essentially, we applied only the orthogonal complement theorem. So we see that actually the orthogonal complement theorem implies the Riesz representation theorem. The Riesz representation theorem. So the final observation is that the Riesz representation theorem holds only if H is complete. Well, indeed, H star is always complete because it is the dual space. And R is an isometry. So if such an isometry exists, then H is necessarily complete. And we have this implication. As a result, we see that all three statements about an inner product space are equivalent to each other. So an inner product space is complete if and only if the orthogonal complement theorem holds for H, and if and only if the Riesz representation theorem holds. Okay. So the next lecture will be in November, and you probably know that in November and December all lectures will be online. So again, the details will be sent by our mailing list. Most probably the lectures will be recorded here at the department and then put to the YouTube channel of the department. Прием задач тоже онлайн.
А семинар?
И семинар онлайн. I'll send the details you in due course, but most probably the seminars will also, the exercise classes will also be online, because so we have about 50 people who attend the course.
You will two groups, but both online.
Probably yes.
С ноября весь матфак переводит?
Нет, переходит. Я думал, вам уже просто объявили это еще, значит, еще нет. Значит, правила такие, что, во-первых,